Exploring city layouts, a new approach to child development. When evaluating the environmental factors that shape a child's cognitive development, discussions typically center on variables like screen time, nutrition, or literary exposure. However, pioneering breakthroughs in spatial neuroscience reveal a far more permanent, systemic force actively sculpting young neural architecture: the geometric layout of local neighborhood street networks. The physical configuration of a city acts as a continuous, silent cognitive trainer. Within mainstream English language arts, ELA, and developmental spaces, we routinely seek specialized frameworks to expand students' intellectual tools. It is time to look outside at how urban grid patterns and organic road structures structurally alter how children process complex data, build mental maps, and develop long-term spatial intelligence. The grid versus the labyrinth: how city geometry dictates synaptic growth. The human cognitive architecture is a highly adaptive system designed to construct intricate mental schemas based on the structural complexity of its surroundings. When a child navigates their neighborhood, the brain relies heavily on a specialized neural loop known as the retrosplenial complex, RSC, which translates immediate visual landmarks into stable, abstract mental maps. Recent fMRI data proves that this map-based navigation system becomes functionally active in children as young as 5 years old. A landmark global study led by researchers at University College London, UCL, the CNRS, and the University of Lyon evaluated spatial navigation data from 397,162 participants across 38 countries. Using a citizen science video game designed for cognitive mapping research, scientists uncovered a striking neural divergence based entirely on childhood environments. The gridiron constraint: low entropy. Children raised in cities with highly predictable, right-angle grid networks such as Chicago, Manhattan, or Toronto demonstrated significantly lower spatial mapping adaptability later in life. Because grid streets require minimal cognitive effort to navigate, the brain's internal wayfinding systems are left understimulated. Researchers discovered that adults raised in grid environments exhibited navigation skills comparable to individuals 5 years their senior who grew up in non-grid areas. The organic advantage: high entropy. Conversely, children raised in rural settings or cities with irregular, nonlinear, and organic street layouts, such as London, Prague, or Paris, developed vastly superior spatial intelligence. The constant, active negotiation of winding paths, asymmetrical intersections, and varied angles forces the retrosplenial complex to actively build and update complex internal coordinates. Cognitive load theory and biological embedding. To fully appreciate why street geometry dictates neurodevelopment, these spatial dynamics must be analyzed through cognitive load theory, CLT, and the neuromorphological impact of neighborhood design.
1.
Minimizing extraneous load via traffic calming. Extraneous cognitive load is generated by environmental stressors that drain working memory capacity without contributing to productive learning. When a neighborhood layout prioritizes wide sidewalks, traffic calming visual cues, and pedestrian protection, a child's brain registers safety. Conversely, high-density, car-centric street designs flood a child's working memory with a constant state of alert. Recent high-resolution neuroimaging studies published in Science analyzed the brains of over 2,300 preteens, revealing that neighborhood stressors become biologically embedded in children's brains. MRI scans show that children exposed to highly chaotic, stressful neighborhood conditions develop observable structural alterations in the prefrontal cortex and the hippocampus, the precise brain regions responsible for language, memory, and executive reasoning.
2.
Maximizing germane load for structural reasoning. When urban environments lower extraneous friction, a child's limited working memory capacity shifts seamlessly toward germane cognitive load, the productive mental effort used to build complex cognitive schemas. Children allowed to engage in active, independent exploration develop enhanced white matter organization and structural integrity. Neuroscientific data demonstrates that higher neighborhood opportunity and walkable, stimulating spaces correlate directly with greater fractional anisotropy, FA, in the superior longitudinal fasciculus I, SLFI. because the SLT5 tract regulates reasoning, spatial attention, and memory consolidation. Optimizing this neural highway yields substantial, measurable gains in a child's crystallized cognition and long-term experience-based abilities. Practical pedagogical tools for spatial scaffolding. For families and educators navigating highly uniform, rigid grid layouts, purposeful, play-based interventions can be introduced to deliberately challenge, stimulate, and strengthen these vital spatial processing pathways without relying on specific urban geometries. Multimodal road and map carpets. Integrate open-ended, nonlinear play rugs featuring organic, winding road maps into early childhood spaces. Using toys to map nonlinear travel routes, invent complex navigation strategies, and narrate stories across irregular lines forces children to bridge abstract visual logic with physical spatial planning. Tactile 3D logic puzzles. Utilize three-dimensional block layouts and town-building puzzles that require children to manipulate, orient, and fit dimensional structures within a fixed map grid. This process exercises structural analysis, geometric reasoning, and spatial foresight. Active wayfinding challenges. Transition traditional neighborhood walks into intentional mapping exercises. Have children lead walks home relying entirely on structural landmarks rather than street names, or challenge them to draw comprehensive maps of their local neighborhood from memory to visually track the growth of their internal mental modeling. Conclusion: collaborative ecosystems for cognitive urbanism. Recognizing the direct link between street geometry and neural development reframes the conversation around urban environments. It shifts city design from a purely architectural task into a wonderful opportunity to support childhood cognitive health. Child-friendly design frameworks, such as the global guidelines established by the National Association of City Transportation Officials, UK, do far more than just creating physically safe walking paths. They help build inspiring, complex, and cognitively enriching urban ecosystems explicitly engineered to help our children's minds thrive. Visit positivelinguist.com for more blogs and further reading.